So let's talk about electron configurations in this video. Just a quick review. Orbital diagrams are maps of where each electron resides in the atom. In order to correctly map your electrons, you have to follow 3 rules. The first, the Pauli exclusion rule, where you have electrons that have equal but opposite spins and are represented by arrows. And each space, so each one of these orbitals, can only have 2 electrons maximum. And one must go up and one must go down. They can never go in the same direction. Number 2 is off-bow principle. You have to fill the lowest unoccupied orbital before moving to the next orbital. So you have to start from the bottom and work your way up. So if you see this first example, you put one electron on the bottom and then another electron on the second. You can't do that. You have to completely fill the lowest unoccupied orbital first before moving to the next level. And finally, the Hund's rule. According to Hund's rule, if there are more than one orbital in the same energy level, so for example, the p orbitals and the d orbitals, you have to put one electron in each box before you start to pair. So for example, this one had 4 electrons, so you must fill in 1, 2, and 3, then start to pair once you have the 4th. This is wrong because they started to pair immediately. Okay. So let's go ahead and do a little bit of practice on how to do orbital diagrams. The first step you would have to find is how many electrons are in each atom. So boron has 5 electrons. Okay, so first we have to fill the lowest unoccupied, which is the 1s, and that occupies 2 electrons. Okay. I've used 2 out of the 5. I have still 3 left. So I'm going to go on to the 2s. 1, 2. And now I have 4 electrons, and I have 1 more electron left for boron. And we'll put that in the next energy level. And there's my 5. Again, this time calcium. In calcium, we're going to look at how many electrons are in calcium, and it has 20 electrons. So we're going to go ahead and fill the orbital diagrams. So the first one is 2. Then I'm going to put another 2, and so I've used 4. Now I'm going to use 1, 2, 3, 4, 5, 6. So far, I have a total of 2, 4, 6, 8, 10, and I still have 10 more because I've only used 10 out of 20. So I'll put 2 here. 1, 2. Now I have 12. 1, 2, 3, 4, 5, 6. Oh, and I just did that incorrectly. I should have done 1 in each box. So far, though, I have used 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. 18 out of 20, which means I have only 2 more left. So I'm going to go ahead and put 1, 2. I have completely put all my electrons onto the orbital diagram. Now, electron configurations takes account for all the electrons that are present in the element in the orbital diagram. And so if we wanted to write the electron configuration for boron, it basically tells me what electrons resides in what orbitals. So for boron, I have electrons in the 1s, and there are 2 electrons in the 1s. Then I have electrons in the 2s, and there are 2 of them in there. And then I have 8 electrons in the 2p, and there's only 1. If you add up all these electrons on the top, the superscripts, they should add up to 5 electrons, which is however many electrons are in the atom for boron. Similarly, for calcium, we're going to take account for all of these electrons. And remember, there has to be 20 electrons. So when I write this, I'm going to start again with my lowest energy level. So that is 1s, and there are 2 electrons there. The next one is 2s. There are 2 electrons there. Then I have my 2p, and there are 6 electrons there. Then I have my 3s, 2 electrons, 3p, 6 electrons, and 4s. 2 electrons, sorry. So if we add all of these superscripts up, it should all add up to 20 electrons, like in calcium. Okay. Now, how do we do electron configurations without having to do the orbital diagrams? Well, the first step we have to remember is that each orbital has a maximum amount of electrons they can hold. So for example, s orbitals can only hold two electrons. P orbitals, since there are 3 p orbitals for every energy level and 2 electrons in each p, you can have 6. For D, there are 5 types of orbitals, and there are 2 electrons in each, so you can have a maximum of 10. And finally, F has 7 types of orbitals, and each can hold 2, so you have a total of 14 electrons. Okay, keep this in mind. Here are the energy levels of the orbital diagram in the correct order. This time I just wrote them out sequentially. And so if you notice, I have these blank orbital, like where we can fill in. And so one thing we need to remember is what are the maximum electrons that can hold. So for this S, the maximum number of electrons is 2. Again, the maximum electrons for this 2s is 2. P is 6. S is 2. P is 6 according to our table. S is 2. Oh, here's our first D, and this can hold 10. P can hold 6. S can hold 2. Again, here's another D. This can hold 10, and P can hold 6. So keeping this in mind, this should help us really figure out how to fill in the electron configuration without having to do the orbital diagrams. So let's do a couple practice. So for every single one of these, we always have to look at how many electrons there are. So if we look at nitrogen on the periodic table, it should have 7 electrons. So let's go ahead and fill this out. So we know there's 7 electrons. S can hold 2, so I'm going to go ahead and put 2 here. And then I've used 2 out of the 7, so I have 5 more. Here's another 2. And now I've used 4 electrons so far. 2 plus 2 is 4. That means I have 3 more left. And so I'm going to go ahead and put the last 3 in this p orbital since the maximum is 6. So the electron configuration for nitrogen is 1s2, 2s2, 2p3. For fluorine, fluorine has 9 electrons. And so I'm going to go ahead and do the same process. So I'm going to put 2 here because it can only hold 2 in the S. Another 2 because it can only hold 2 in this S. So far I've used 4 out of the 9. Now I only have 5 electrons left. And since this p orbital can hold 6, I can go ahead and write 5 since it's less than 6 into this orbital. So the electron configuration for fluorine is 1s2, 2s2, 2p5. Now let's go ahead and try sodium. Sodium has 11 electrons. I'm going to go ahead and fill this out. 2. So far I've used 4 out of the 11, so I have 7 more. But 7 is greater than 6, so the maximum I can put here is 6. So far now I have used 10, and I have 1 more left over, so this is 1. So again, total 2 plus 2 plus 2 plus 6 plus 1 is equal to 11 electrons. Okay, now finally, let's go ahead and do one last example. What about sodium ion? This is Na+. Remember, the plus sign means we have lost an electron. There are more protons than electrons. And since this is just plus, that means we only lost 1 electron, which means sodium ion has 10 electrons. And when I fill this out, I'm going to go ahead and fill out 2, and there's 4. I have 6 left, so I'm going to put 6. And this is the electron configuration for the sodium ion. 1s2, 2s2, 2p6. And again, now this is a total of 10 electrons. Now, when we look at ions, you're going to notice some of them are going to all have the same number of electrons. For example, we have nitrogen minus 3. It has 10 electrons. Fluorine minus 1 is 10 electrons. Neon is a noble gas and is not an ion, but it has 10 electrons. And sodium ion has 10 electrons. So when we do the electron configurations for all of them, they all have 1s2, 2s2, 2p6 as their electron configuration. And this is called isoelectronic. It's when all the species have the same number of electrons. Electron configurations can get very long. As you can tell here for ruthenium, which has 44 electrons, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 46. That's a pretty mouthful, and also when you're writing out, a handful. So we can do a shorthand. You can do a shortcut, and this is called a noble gas abbreviation. The noble gas abbreviation for ruthenium would be krypton in brackets 5s2 46. Now there's a reason to why we have to do this in this format, and let me go ahead and explain to you why. First and foremost, you need to be able to show all the valence electrons in the atom. Okay, and that's why we take the highest energy level and still state the highest energy level, and then put the noble gas abbreviation to account for all the inner electrons. And so we have to think about this in the Bohr model. Okay, so let's go ahead and do our first example, which would be oxygen. Okay, so let's do the electron configuration for oxygen, and that happens to be 1s2, 2s2, 2p4. Okay, there's a total of 8 electrons. Okay, now when we do the noble gas abbreviation, we're going to go ahead and look at the noble gas in the row above. Here's helium. If you notice, helium has a total of 2 electrons. Here is my total of 2 electrons. So what I'm going to do is I'm going to go ahead and replace helium 1s2 with helium in bracket to represent the 2 electrons, and then write the rest of the electron configuration that's left over. And so this is how you would write the noble gas abbreviation for oxygen. The next one we should try is phosphorus. Okay, phosphorus. And it has a total of 15 electrons. So the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. Okay, now we're going to go ahead and take a look at the noble gas in the row above. That is going to be neon. If you notice, neon has 10 electrons. So I'm going to go ahead and count up 10 electrons here. Here's 2, 4, 10. This time neon represents these 10 electrons. So what I'm going to do is I'm going to go ahead and write neon in brackets and replace these 10 electrons and then write the rest of it out. So it's 3s2, 3p3. Okay, and so this has this is the noble gas abbreviation for neon. For phosphorus. Now what happens if your element happens to be a noble gas? So let's go ahead and do neon. Okay, neon has 10 electrons, and its electron configuration is 1s2, 2s2, 2p6. Now, I can't just put neon in brackets. Okay, not allowed. Okay, and that's because it doesn't show me the valence electrons in the highest energy level. So we still have to look at the noble gas in the row above. So that means helium is going to be our noble gas in the row above, and so it has 2 electrons. So I'm going to go ahead and put helium. And since that has 2 electrons, we're only replacing this and still have to write the 2s2, 2p6. Okay, and so the last thing I'm going to teach you is how to determine how many valence electrons there are based on the electron configuration. So just recall, valence electrons are the electrons in the outermost shell. So they're going to be in the highest energy levels. So let's go ahead and look at sodium's electron configuration. It is 1s1, 1s2, 2s2, 2p6, 3s1. Okay, now if we look, our highest energy level is 3. Okay, the next one is 2 and then 1. So our highest energy level is 3. And the only 1 electron exists in this highest energy level. So therefore, this has only 1 valence electrons. Okay. Okay. So let's do another example. Go ahead and look at gallium. It has 31 electrons, and its electron configurations is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p1. If you notice, our highest energy level is 4. Okay, so if we look only at the electrons in the highest energy level, which is 4, there's 2 in the s, 1 in the p. This tells me how many valence electrons I have in the highest energy level, which is 2 plus 1 equals 3 electrons. Okay. The next one we have is scandium, which has 21 electrons, and its its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. And now we're going to look at the highest energy level. Look, again, it's the highest energy level is 4. This is a 3, so we can't count that. So our highest energy level is 4. Therefore, our valence electrons for this should be 2 electrons. Now it's your turn to practice on your worksheet, and you need to go ahead and write the long configuration, the shorthand configuration, and how many valence electrons are in the atom.